Hey kiddos, here we are. We're going to talk about quadratic transformations. You should have done some of this today while you were in class. You should have done a Desmos activity with your phone following the directions that were on your page. If you did not do that today, I expect that you will sit down before you come to class and you will do that tonight, and that will be completed when you come to class because that is going to help you understand the things that we are doing. So please make sure that you do that. That is an expectation. It is part of your grade for this week in your packet. So we're going to talk about transformations. We're going to do, your notes for this are 2 pages front and back. We're going to do the first page front and back today. We'll do the second page front and back tomorrow. And so here we go. A transformation is the change in the size, the position, or the direction of a figure. So it changes the size, it changes where it's at on the graph, or it changes the direction it is facing. A stretch or compression, these are going to be what we talk about tomorrow, but a stretch or compression makes the graph wider or narrower. And a translation, which are the things we're going to talk about today, moves the graph either up or down, or it moves it to the left and right. And so we're going to talk about both of these translations today so you can see them. And then tomorrow we'll do the compressions. So if you have your calculator, it will come in handy. So the first thing we're going to do is taking our x squared, our parent function, and adding or subtracting a number to it. So if I've got x squared and x squared plus 3, let's look at them on our calculator. So I'm going to go into y equals, and I'm going to put x squared into the first one, and into the second one I'm going to put x squared plus 3. And I'm going to graph them so I can see the two together. So there's my parent function. The vertex is right here at 0, 0. It opens up to the left and right, so I've got a domain of all real numbers. And then my new function, the red one, its vertex is at 3, 0. So what has happened is I've taken my parent function and moved it up 3. So this, when I add that plus 3, so I take the x squared and I do plus 3, then I take the graph and I translate it up that many units. So when I do x squared minus 3, and I'm going to put it in here because mine is color, I'm going to put it in as the third one. So I'm going to do x squared minus 3 so you can see all three at the same time. Here will be the x squared minus 3, and so I've got my parent function in blue with the vertex at 0, 0, my x squared plus 3 with the vertex at 3, 0, and then my x squared minus 3 has a vertex down here at negative 3, 0. So that translates it down. And so when I add a number to the thing that is squared, so when I add a number to the x squared, what it does is it moves it up. When I add a subtract a number from the x squared, it moves it down. So the question is, do these change the domain? Well, here's my graph. They all open or concave up. They all go to the left and to the right as far as possible. So all three of these graphs have a domain of all real numbers. So no, they don't change my domain. But they do change the range. The range of this one is going to be y is greater than or equal to 0 because that's where my vertex is. The red one becomes y is greater than or equal to 3 because of where my vertex is. And the black one is y is greater than or equal to negative 3 because of where my vertex is. So yes, translating it up and down does change my range. So the domain doesn't change, but the range will. So here's the next question. I've got x squared plus 3 and x squared minus 1, and I want to know how they're related. And all they're going to do is give it to me in terms of f of x and g of x. Well, if I go from plus 3, which moved up, to negative 1, which moved down, what I have is a graph that was up here at plus 3 that moved down here to negative 1. And so it has, this is f of x, and this is g of x, and so what has happened is it has moved down. So f of x is above g of x, and I've got to figure out the distance. Well, from positive 3 to negative 1 is a distance of 4. There are 4 units in there because if I count 3 to 0 makes 3, down to negative 1 is 1 more, so 3 plus 1 is 4. So here are my options. It says it's 4 units to the left. Well, no, I didn't go left. 4 units to the right. I didn't go right. Now I've got 4 units below or 4 units above. So I've got to read how it's worded. It says f of x is 4 units below or f of x is 4 units above. Well, if I look at how my stuff is related, f of x is up high, g of x is down low. So f of x is above g of x, so my answer is D. So number 3 asks, how would the graphs of x squared minus 15 be affected if I change it to x squared plus 7? Well, again, if I have a graph, that means that my first one's down here at negative 15, and I'm going to move it up here to positive 7. So I'm going to slide it or translate it up. So it's going to go up. It's not going to go down, left, or right. All of the numbers are the same. So A is the correct one because I'm moving it from negative to positive. It goes up. And it goes up 22 units because that's how far apart these two numbers are on a number line. So let's talk about the difference between adding and subtracting a number to the x squared. So I have the function x squared plus or minus a number, to taking the function and adding or subtracting the number inside with a quantity and squaring all of it. And so I'm squaring even the number that's being added or subtracted. So now I'm going to do x squared and then the quantity x minus 2, all of that squared. So if I go back here to my calculator, I'm going to leave y1 the same. My y2 is going to be the whole thing x minus 2 squared. And so I'm not just squaring the x, I'm also squaring this 2. And so when I look at this picture, my parent function stays the same, concave up, vertex at 0, 0, but that x minus 2 now takes my new function and it shifts my vertex to the right, and now my vertex is at 2, 0. So it didn't move it up or down this time. When I take that minus 2 and I put it inside the quantity and square the whole thing, this translates it right. So it does exactly the opposite of what you would think, because when it goes minus, you want to say that it translates left, but this minus also actually moves it to the right. So now let's do the x plus 2. So I'll go to y equals, and again, I'll put this one in here so we can see all three at the same time. This time I have x plus 2, the whole quantity squared. And when I graph that one, I have my original two functions, and now this one has gone from the parent function to the left. So now when I put that plus 2 in the quantity and square it, it translates it to the left that many units. So this one went to the left 2 units. So the question is asking, does my domain change? Well, all three of these are concave up. They all go to the left and to the right as far as possible, so they all have a domain of all real numbers. So again, no, my domain doesn't change. The question is, did I change the range? Well, if I look, this one has a vertex at 0, 0, so its y is greater than 0. This one has a vertex at 2, 0, and it opens up, so the range is y is greater than or equal to 0, because the y value is still 0 here. Same with this one. This one is also y is greater than or equal to 0, because I have my y value, my vertex is still 0. I didn't slide it up or down. I didn't change the y value of that vertex at all. So no, the range also does not change. So number 5 here asks, in what way does the graph of x minus 5 quantity squared differ from the graph of the function x squared? Well, this is your parent function x squared, and I'm going to take it, I'm going to do minus 5 and square all of it. I'm going to do x minus 5, all the whole quantity squared. This minus 5 moves it left. Sorry, it moves it right 5 units. See, it does just the opposite of what you want it to do. That minus does not go to the left, even though you think negatives are left. That's not what happens. What happens to the graph, as you saw when you tried it and you played around with it, is it actually shifts it to the right. And so this f of x minus 5 should be translated 5 units to the right of f of x. So if you look at it, this one says 5 units up, this one says 5 units down, this one says 5 units right, so there it is, and this one is 5 units left. So number 6 is going to put it all together. I have x squared, and I'm going to translate it 7 units left and 5 units down. So I want a new function. Well, 7 units left takes that 7, and it puts it inside the parentheses to be squared. And because it went left, it is a plus, so it puts it all together in here. This 5 units down becomes just a minus 5 along with the thing that's squared. So I'm subtracting 5 from the whatever is squared. So I have this part moves it left, this moves it down, so my function should be C. So number 7 here, for the functions h and g, which statement is true? H of x is equal to g of x plus 14 minus 12. Well, this plus 14 goes left 14 units because of the plus, and this minus 12 goes down 12 units because of the minus. So what I want to look at, I need to see that h is the graph being translated 14 left and 12 down. Well, this says 14 down, sorry, 14 right and 12 down. That's not correct. This one says left 14 and down 12. That looks like it matches. Right 14, nope, that's the wrong direction. left 14, up 12, that's also the wrong direction. So the answer is B. So the next question I have, how do these compare? X minus 1.6 quantity squared and x plus 4.7 quantity squared. How do they relate to each other? Well, I'm just going to look at them on my graph. So I'm going to go to y equals. I'm going to clear out everything that's in here. And I'm going to put in those two functions. So this one is x minus 1.6 squared. So I'm going to do my x minus 1.6 squared. And then I'm going to do my x plus 4.7 squared. And when I look at the two, since mine is in color, it'll be real easy to see. Here's my x minus 1.6, and here's my x plus 4.7. And so you should be able to see that g of x is shifted to the left of f of x. So g of x is left of f of x. And if we want to know exactly how far, we've got to figure out how far it is from 1.6 to negative 4.7, because that's where they are. This went right, so it's right here at positive 1.6. This one went to the left, so it's at negative 4.7. So if I find the distance between those two, so I have 1.6 minus, clear my screen, 1.6 minus my negative 4.7, because it was negative. That's how I find my distance. They are 6.3 units apart, and so it is 6.3 units left of f of x. So that's what it's asking for. You don't necessarily have to give me the distance between the two, but it's kind of nice because, as you noticed, it will ask those questions in very specific terms like that when you see them. So this is what we'll practice tomorrow when you guys come to class. If you try to go ahead and do the practice that's in your package, you might get a little lost because it combines everything. I'm going to give you a different set of practice that you're going to work on when you come to class tomorrow. So I will see you then. Please make sure you have done that Desmos activity before you come to class tomorrow.